In this video, we're going to be covering subatomic particles, atomic structure, and a little introduction into what isotopes are. Now, if I first draw here, just a sort of very simplified version of an atomic structure of an atom here. And I'm first going to show you the different parts of an atom. So here we have the densest part of the atom, which is going to be the nucleus. And here we're going to have the shells, or energy levels, as some people like to refer them as. So, we'll just put shells here. Now, in the nucleus, there are two subatomic particles. One is a proton, and one is a neutron. In the shells, there is only one subatomic particle, and that is the electron. Now, in the subatomic particle, in the atom, the electrons orbit around the nucleus here. But as you envision an electron, don't exactly envision it as a particle per se. Just envision it as a cloud of negativity, right? Because I mean, later on in chemistry, we can get into some other deeper concepts involving wave-particle duality and so forth. But for now, just envision this electron as just a cloud, right? So let me specifically choose an element here on the periodic table. So we're going to go with the simple one, maybe lithium. We're going to go with lithium 7. And what that means is just, well, we'll get into what that means in a second. So I'm going to draw a ring here, but in this ring, I don't mean this ring to be a shell. This is just the nucleus, okay? And I'm just going to draw 3 protons, because we know lithium has 3 protons, and I'm just going to draw 4 neutrons here to make up this 7. And I'm also going to draw, we'll use another colour so it's not confusing. We'll draw the first shell here in blue. And so I'll do the electrons in this sort of colour. So the electrons, maybe drawing crosses. So there's 3 electrons, same number of electrons as there are protons, because this is a stable atom. So let's see what this all means. Now we can always write lithium as this. We can write lithium as Li, and then its mass number here, and its atomic number here. Mass number of lithium, which is 7, is the total mass of the nucleus. And the atomic number, which is obviously 3 here, is the total, it's easier to say the total number of protons. Just draw a little plus charge there. You know they're obviously positively charged. So, well, what do you mean by masses then? What do I mean by masses? Well, if we just scooch over here a second, in the nucleus, now we're going to start talking about subatomic particles here. We have neutrons, and we also have protons. And these each have characteristics of a charge and a mass. So the charge of a neutron is obviously neutrally charged, so it's So you're going to have 0, but of a proton, it's +1, as I've already said. And the mass of both of these is just 1. 1 AU, 1 AU. It's arbitrary units. It doesn't mean anything on this level of chemistry. And in the shells, we have the electron. And now an electron has a charge -1 and a mass of about 1/1800, but that's normally rounded to 1/2000 of a mass, which is why the nucleus, this part here, this nucleus here is the densest part of the atom. So coming back to here, what I mean by the total mass of the nucleus, we can see that neutrons and protons both have a mass of 1. So, because there are 4 neutrons and 3 protons here, they're going to add up to make 7. And that's what I mean by that. So let's look at a different element here. Let's look at helium, just right over here in this corner in the periodic table. Let's look at helium. I'm just going to go with helium-4. So I'm just going to get rid of this stuff here. And I'm again just going to draw this circle here. This only represents the nucleus. This doesn't per se represent any shells at all. And the outer shell I'm just going to draw here. So inside of helium, we have the helium, we have 4 and 2. So just by looking at this here, we can already tell that there are going to be 2 protons and 2 electrons. Why? Because in a stable atom, there are the same number of protons as electrons, because this is not an ion, it's not positively and negatively charged. And we also know that there will be 2 neutrons, because the total mass of this helium atom here is 4. And there are already 2 protons making up half that mass, so there will be 2 neutrons. So we can easily fill this out here as 1, 2. Fill out my neutrons here, 3, 4. And fill up with my electrons, 1, 2. Cool. So one extra thing I did want to look at in this video before we end off here, I wanted to look at isotopes. And I think in this example we're going to be specifically looking at carbon, because carbon's quite an interesting one. We're going to look at 3 main carbon isotopes here. And I'll get to what an isotope means in a second. I'm just going to draw these for you here. 6. So you might have already been able to infer from what I've drawn here, but an isotope, basically they're the same elements, but with different masses. And by masses I just mean different number of neutrons. So you can see here in this carbon 12, which I'm pretty sure is the most common isotope. As you can see on the periodic table, carbon 12 is the most common isotope, and it has the devil's number. So it has 6 neutrons, 6 protons, 6 electrons, 666, right? However, here in this carbon 13, we can see that there's still 6 protons, and this isn't an ion, so that means it's going to have 6 electrons. However, it has a different mass number. And what's 13 take 6? Well, that's 7, so this is actually going to have 7 neutrons. I'm just shortening these to the P, the E, and the N here. And then with carbon-14, you can see that again there's 6 protons, which means there's going to be 6 electrons. But now there's actually going to be 8 neutrons. And so we come to this definition of here, they're the same elements, because they have the same number of protons, but they have a different number of neutrons. And these can have different, some can be radioactive, some cannot. They have varying properties, I would say. However, they all react in the same way. They all react in the same way, and that is because if, for example, I draw carbon here, it's just going to have one outer shell because it's got 6 electrons. I'm just going to draw the 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then I'm also going to draw carbon-13 here. Try not to click on any of my other apps. Right. We'll just, I mean, it's hard to see here how many there are, but this is carbon-12 and this is carbon-13. And you can see here, if I draw the outer electrons, 1, 2, 3, 4. Oh, sorry, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Five, 6. Sorry, just hold on with me 1 second here. Just hold on 1 second with me here. I must apologize to you. I must apologize to you guys right here. So let me redraw these. I've just been completely stupid the entire time here. So we're counting these as shells here. So carbon actually has 4 electrons in its outer shell, and I can't believe I can't believe I've done this here. But okay, so 1, 2, 3, 4, and then we've also got 2 in its inner shell. 1, 2, 2, 1, 2, 3, 4. Then we've obviously got all the protons in here. Bam, 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 bam. Obviously, this isn't an exact representation of all the numbers, but there we go. Now, sorry, that must have been very confusing for you guys, but this is the correct way. Now we can see, because they're the same number of valence of outer electrons in carbon-13 and carbon-12, they both react in the same way. So, for example, you'd say, well, in the combustion of carbon-12 and carbon-13, the same products are produced, and that is because they both reacted in the same way. So, thanks for watching. I hope you've got a better understanding of this. Sorry for my mistake earlier, but it was easily corrected. Obviously, rookie mistake. The first 2 electrons are placed in the first shell. Anyway, I hope you guys enjoyed.